Thanks for your introduction. So my name is Binggao, and actually I'm doing optimization, but not the optimization of shape. We are doing optimization over the manifold. And here I'm going to talk about a special manifold. We call it the symplectic Stiefel manifold. And we think this is a new one, and we developed some geometric tools to this manifold, and we apply it to optimization problem on this manifold. So, okay. And this is a joint work with my former colleague, Thanh, and with my postdoc advisor, Absil, and also with Tatjana from University of Augsburg. Okay. So here is the outline. First, I will give you a short introduction of the symplectic matrices and what is symplectic constraint. And next, I will investigate the geometry of this set and also apply this set to optimization problem. And then I will give you some preliminary numerical experiment on this problem. Okay. So first, let's look at the symplectic matrices. Actually, a symplectic matrices is defined by this quadratic matrix equation here. So we have variable x with double n multiplied with double n, and it has to be satisfied with this equation: x transpose multiplied with omega, and x equals to omega itself. Here we need to assume that the omega is non-singular and also screw symmetric, and then this matrix will be called the symplectic matrices. And actually, this kind of matrices have many applications, such as geometric, numerical integration, and also in the matrix composition, also in some quantum physics, like the quantum optics, and also the quantum information theory. And here we just want to consider a very special case. So let's consider this omega matrix. We consider it as a parameter, and we assume that it equals to this portion matrix. So where In is the identity matrix. So we have omega here, and then this J omega will be orthogonal and also satisfy the non-singular property and also screw symmetric. So, okay. So we assume omega has this form, and then we can define our optimization problem. So our problem is like this. We minimize a continuously differentiable function fx here, but we have a special constraint here. Our constraint is the symplectic constraint. So that means our variable x should satisfy the symplectic equation. And if you write down this constraint, you can see it is like this form, and we have the row number n, and we have the smaller column number p. So it will look like this. And if we assemble all these kind of matrices by SP, then we'll get this set. And in the later, I will prove that actually this set is a manifold. And also, if you carefully choose a metric, then this manifold will be further a Riemannian manifold. Okay, so there is one very special case. So when your row number equals to your column number, then you will have the classic symplectic group, the SP, like this. So why we consider about this problem? So first, this optimization problem is non-convex. So in the optimization, usually non-convex means difficulty. So we have many local solutions. We cannot find the global solution. And secondly, actually, this set has not been developed or studied. And also, for this kind of problem, for now, there is no general algorithm for it. So that's our motivation. So before we move into the detailed geometry, I want to give you some introduction on the applications. So I think this is very important. So it motivates our research. So first one is a projection problem. So consider we have a distance function here, and we want to compute a projection of a matrix, any matrix, to project this matrix to the set of our symplectic matrices. So how can we do that? So we need to solve this optimization problem. So you may think, so is this problem has a closed form solution like the orthogonal case? So as we know in the Stiefel manifold or the orthogonal matrices, we know that the single value decomposition is a projection. Okay, so but in this case, we don't know the closed form solution actually. And there is a very special case if we consider many data points here and we compute the mean problem. So then finally we can get this kind of problem, and this will be the real problem in the real application, like the physics. Okay. And another important application is in the numerical linear algebra. So consider that we have the Williamson theorem that says that we have a symmetric positive definite matrix. And actually there is a decomposition like this, and where X is a symplectic matrices, and you have a diagonal matrix D here. Then we call this the entries of the diagonal matrix is symplectic eigenvalues. That means it is actually a special kind of eigenvalue problem. And so we know that any eigenvalue problem can be transformed into a trace minimization problem here. So we minimize this trace operator with this quadratic function, and then we can find this eigenvalue, the solution of this eigenvalue problem. And also we have some generalization. If we consider more general optimal quadratic function, and we can minimize this kind of function subject to this constraint. Okay, so another class of application is in the dynamic Hamiltonian systems. So actually, we have a dimension n system, and we want to reduce order of this Hamiltonian system. And at the same time, we want to preserve the structure of this symplectic constraint. So that means we need to solve this projection problem subject to this symplectic constraint. So, okay, so that's all the applications inspired our work. And here are some literature reviews. Actually, in the literature, the work either focus on the symplectic group, which is a very special case. You have the same row number and the column number for the matrix, or they works on the special application. That means you have a very special structure of your objective function. Okay, so for now, I think there is no general algorithm for this type of problem. So we will investigate this problem. So first, we want to investigate the geometry of this set. Okay, so why are we interested in this geometry? So as I mentioned, I'm doing on the optimization over the manifold. As you know, it is a curved space, and it has tangent space, and we can search along the tangent space. But if you search along the tangent space and the new point will not belong to the manifold. So if you want to get a feasible algorithm, you need to project your tangent vector back to your manifold. So that's the main point here. We need to develop some projection to project the point in the tangent space back to the manifold. So that's the main idea of the optimization algorithm on the manifold. Okay, so first let's look at this manifold, and actually this manifold is very similar to the classic Stiefel manifold. It is an orthogonal matrix, and this manifold has been studied before, but they use a very different and abstract way. Here we use this matrix formulation, and it is very simple. And we prove that this set SP is a closed embedded submanifold of the whole space. And also it has the following dimension. Okay, so now we have the manifold, and so what's the difference? So actually, it is some annoying property of this manifold. So you know that for an orthogonal matrix, it is obviously bounded. So, but for this manifold, it is unbounded. So let's look at a very simple example. If you consider the orthogonal group here, so actually it is compact and with dimension 1. But if you consider this symplectic counterpart, you will have it has dimension 3. And actually, this kind of diagonal matrices belong to this set, and you will find you can, for any arbitrary real number, can satisfy this constraint. That means your set is unbounded. So this is a very bad property when we do the optimization. So in the optimization algorithm, we usually want your iterate sequence to be bounded. That can guarantee you have the convergence results, you have bounded iterate, so that's fine. But here we have an unbounded set, so that's a difficulty. And also, as I mentioned, the projection to this set does not admit a non-closed form solution. So that's another difficulty. Okay, so first, this is the standard derivation. We have the manifold, and we can compute its tangent space, and we have different formulations. The first one is like the decomposition form, and the second one is another formulation. Okay, so that's for the tangent space. When we have the tangent space, we can equip this manifold with a metric. Okay, this is natural. And the most natural metric, I think, in the Euclidean space is the Euclidean metric. Namely, this Frobenius norm of a matrix. So we consider the trace operator here, and we have this metric. And in view of this metric, we can have the normal space, and we can also have the projection of this manifold. We can get the projection onto the tangent space and also to the normal space. Okay. So actually, you can find the projection does not admit a closed form solution. If you want to compute the projection onto the tangent space, you need to solve an equation, a Lyapunov equation like this. And so this may be not convenient in our practical computations. So we consider other metric. So I won't go to the detail of this metric, but in this metric, we can have the explicit projection, but you don't need to solve an equation here. Okay, so we have the metric, we have the tangent space, we have the normal space. You can have the gradient. So we're considering about the optimization problem. So you have the objective function, and you have the gradient of this function, but it is not in the tangent space. You can easily project this your gradient back to the tangent space. Okay, so this is a standard. Okay, so now we have the gradient, we have the tangent space, we can do the optimization on this manifold. So basically, we can consider any line search algorithm, so sometimes called the gradient descent method, and we can search along the tangent space. Okay, so now your new point will not belong to the manifold, and then we choose the step size and project this tangent vector back to your manifold. Okay, so that's the classic Riemannian gradient method for this problem. Okay, so now there is only one question: how can we choose this projection? How can you guarantee your tangent vector can be projected to your manifold? So there is two ways we can define it. The natural way is to consider the geodesics. So the most natural way. So we compute some geodesic, and we do some simplification, and we get the following quasi-geodesic curve, and we search along this curve. That means we can search along on the manifold. Okay, so that's one projection. So another is you can consider a matrix transformation, like the Cayley transform. If you do the Cayley transform, then your new point will still belong to the manifold. Okay. So now you have the projection, you have the gradient. You can do any optimization method. And so here is some basic numerical here. You can see we optimization a function, and the gradient of this function can be reduced, and also in times it has a very good performance. Okay, I think I have one application here. If you consider the eigenvalue problem, you can see if you use the Long-Schulz method, symplectic Long-Schulz method, and if you use our method with different metric, you can get the very comparable singular eigenvalues. Okay, I think I will stop my talk here. So in this work, we consider a new manifold, and we consider the Euclidean metric, and we develop some geometric ingredients. So in the future, maybe we can extend our work to other more general Lie groups, and also apply to other applications, also investigate some second-order geometry. Okay, if you are interested, my talk is actually based on the following reference, and the first one is our conference here, of course. Okay, thank you. Thanks for your attention.
Are there some questions?
Yes.
Yes, can you use it?
Simple question.
Mm-hmm.
Do you have a complex manifold analog of this?
No, we don't have the complex.
But it would seems like a complex manifold would have this structure, maybe.
Yes, maybe, but we still didn't consider the complex case. It's more complicated. Yes, problem.
Some other questions? There is no question on the chat. Yeah. Yes, please.
Okay. Thanks. You said you were able to find a retraction using quasi-geodesics.
Yes.
And so using an actual geodesic is too complicated.
Yes.
And do you know like how good the quasi retraction would be with respect to maybe a retraction based on geodesics?
Yes, actually, in this quasi-geodesics, we actually in the geodesic equation, it is very complicated. It has a very complex derivative here, and we just simply reply this derivative with a second-order derivative, classic second-order derivative, and we solve this equation, and we incidentally get this quasi-geodesic curve. But we prove that actually this curve can preserve the manifold structure, and we plot some feasibility violation, and it can preserve the manifold structure very well. Okay, and so in the computational aspect, there is only one matrix exponential here. Okay.
Okay. Yeah. So that's good. Okay, thanks.
Thank you. I think there is one question by Zoom.
Mm-hmm.
I saw someone to activate his microphone. Which one it is?
Can I ask a question?
Yeah.
Okay, yeah. Very nice talk. So may I know, like, do you have any convergence guarantees for your gradient descent algorithm?
Yes, yes, we have convergence, global convergence results for this kind of gradient algorithm, but we didn't show here. In our paper, we have the convergence results for this algorithm.
Okay. So the other question, like you said that you have two metrics, to choose
Yes.
with. So why you? So do you have any motivation on this, like, different metric? What's the difference between them?
Yes. Here you can see we have different metric. And actually, in the natural Euclidean metric, we know that the projection onto the tangent space and the normal space does not admit a closed form solution. That means if you want to compute the projection, you need to solve an Lyapunov equation. So this is inconvenient in our algorithm. So that inspires us to develop another metric. If you use this new metric we defined, then you will get your projection, and your projection onto the tangent space is closed form. That means you can just compute this projection without any equation here.
So using your metric here, this this projection operator becomes easier.
Yes, that's the main point. Yes.
And this metric is created by you.
Yes, we developed this novel metric.
Okay. Very nice.
Thank you.